Hello everybody, this is Professor Lombardo. In the next series of videos, I want to go over some more examples with the normal distribution, but this time I want to focus on the process of finding things like percentiles, top 10%, middle 20%. In other words, the process that we described in class is going from a probability to finding a score. Our primary tool today is an Excel command called NORM.INV. Now you'll recall from our last class that we were using norm.dist. Now a norm.dist, given a particular score value, will tell you the probability that's in the tail for a particular normal distribution. And we looked over different pictures and we kind of talked about how the Excel command relates to finding probabilities if you know a score. Today we want to switch that around. We're going to start working with this norm.inverse function. So this will be our Excel command. And instead of knowing the score or the value along the horizontal axis, we're actually going to know the probability in the tail. And what the norm.inverse function is going to do is essentially tell us what the score is that has this probability to the left. The first type that we're going to interact with is a percentile, or a bottom k% of a normal distribution. Fundamentally, what we're trying to answer here is what score has k% to its left? Or in other words, for what score can we expect k% of the other possible scores to be smaller? All right, so again, this is equivalently called the kth percentile for x. And the important thing to note here is we're looking for a score. We're not looking for a probability, we're looking for an actual measurement value. Right? When somebody says find the 30th percentile, it tells us that 30% should be sitting in this little left tail. We're going to use norm.s.inverse to find the appropriate z-score, and then we're going to convert it back up to the original units. Now the reason that I do this is we'll use norm.s.inverse later in the course. I will show you a shortcut that just uses norm.inverse, but for now let me show you this process here. All right, so let's jump to an example. So we're inside the week 7 day 1 Excel worksheet. We're in our top percentile example sheet, and we want to work through this particular example. So we assume that we have a normal random variable. It has a mean of 35 and a standard deviation of 7.6. All right, so these are the parameters of our normal random variable. And we can use them to answer questions like we were considering last class. Like in this case, we're looking for what's the probability that x is between 27 and 45. So if we write this symbolically, we'll just do a little bit of a review here. Right? We can write it in terms of inequalities inside of a percent. So using the appropriate z-scores, what we would do here is take 27 and 45, and we would convert these to z-scores by taking the measurement minus the mean and dividing by our standard deviation. And then we can do the same thing on the other side. Remember that putting the difference between your measurement and the mean is very important. So you have to make sure that is inside of parentheses here. All right, so the equivalent z-scores would be negative 1.05 less than or equal to z less than or equal to 1.3, let's call it 2 since we'll round up. And then remember from last class we described how we have to write these things in terms of cumulative probabilities. So in other words, it has to be of the form probability that z is less than or equal to a single number. So when we're dealing with these in-between probabilities, this is the easy way to do this. You take the larger cumulative probability and you subtract off the smaller. And the idea is each one of these cumulative probabilities corresponds to, oops, that's going to give me an error. All right, each one of these cumulative probabilities corresponds to a norm.s.dist command. Okay? So for this first one, z being less than 1.32, we would do norm.s.dist, right? We use the .s because we're talking about the z distribution. 1.32 comes first, and then our cumulative argument's always true, right? Minus. Now we have a norm.s.dist command for the second one, norm.s.dist. negative 1.05, and again, the cumulative command is always true. So when we hit enter here, this will be the probability that a random score falls between 27 and 45, assuming that those scores have this normal distribution. Okay? Now we're trying to go the other direction here. Now we want to find the 77th percentile, right? So in other words, for what score, let's call it P77, is the probability that x is less than or equal to that 77th percentile equal to 0.77. Okay? Now, this is sort of a complicated way to think about it. The easier way is to think about this in terms of a picture. All right? So just as I had recommended last time, always draw little pictures when you start working with the normal distribution. So in other words, here I have my normal distribution. It has a mean of 35, so the peak here would be roughly around 35. And a standard deviation is 7.6, so that, again, sort of adjusts the width or the wideness of this normal curve. We want to know what score, so in other words, how would we label this horizontal axis down here to guarantee that 77% is in the left tail? That's what a percentile is asking. Right? So when we look at this picture, how much area is to the left? All we have to do is look at the picture that we drew and we labeled. So in this case, we've got 0.77 to the left. We have an area of 0.77 to the left. Okay? Now this is critical because the area to the left of the score you're trying to find has to be the content of your norm.s.inverse function. Okay? Just as the norm.dist only finds left-hand cumulative probabilities, the norm.s.inverse is only going to find scores with a particular probability to the left. All right? And this is demonstrated by the following picture. If we know the probability to the left, we can use that inside the norm.s.inverse and return the actual score that kind of marks that off. Okay? So, to find the appropriate z-score, we're going to use norm.s.inverse. And then inside of our inverse command, we're going to put the left tail area. And you'll notice with our little prompt, it doesn't ask for anything else. Okay? So if we were dealing with the standard normal distribution, this particular z-score would have an area of 0.77 or a probability of 0.77 to the left. Okay? So this here, this is a z-score. So we have to convert. We have to convert our z-score into a corresponding x value. Generally speaking, our formula for a z-score is z is equal to x minus your mean over your standard deviation. Now, if you solve this for x, in other words, multiply both sides by sigma, you can get the reverse formulation where if you know a z-score, you can get your actual score. And it looks like sigma times your z-score plus your mean. So to get this, all we have to do is take our z-score times our standard deviation, which from above, remember, was 7.6, and then add the mean. In this case is 35. So this would tell us a score of 40.61. I'll just cell reference. 40.61 would have set 0.77 area to the left. In other words, if I were going to label this picture here, this would be roughly 40.61. Okay? So this is how we work with percentiles. Now the shortcut here, which essentially just erases the need to find a z-score and then convert it, is to just use norm.inverse. We can use the same probability of 0.77, but this time we provide the mean, which is 35, and the standard deviation separately, and it'll automatically do the conversion, so we'll end up with the same answer. So when finding a percentile or a bottom k% for a normal distribution, this is very straightforward. The percent, the k%, the k, is exactly the input to the norm.s.inverse command that you're going to use, or if you use norm.inverse, it's the first argument. And this will give you the appropriate score or the appropriate z-score associated immediately. Now, less obvious is when you're looking for a top k% of a normal distribution. Now notice the difference in the picture. The percentage that I'm referring to, the top k%, isn't going to the left, but rather to the right. So I have to do a little bit of a switch around here. Okay? Since norm.inverse or norm.s.inverse all work with probabilities to the left, I have to think about, if I'm looking at the top k%, how much ends up being to the left-hand side. So you have to do a little bit of math here. Equivalently, you think of the top k% of a normal distribution as being the same as the bottom 1 minus k, or 100 minus k, depending on whether k's in terms of a decimal or not. Okay? Then the process is exactly the same. Once you know the area to the left, you can use norm.s.inverse to find the appropriate z-score, etc., etc., etc. Okay? So let's do another example here. Find the score. So we're dealing with the same random variable, has a mean of 35, has a standard deviation of 7.6. But this time we want the score that marks the beginning of the top 7%. Right? So I've drawn a little picture here for our second example. Right, same basic idea. We've got our normal distribution. The mean's roughly about 35. The standard deviation is determined this width over here. Here's the score we're looking for. We want to know where along the horizontal axis does this transition occur, where you have 7% above, right? So keep in mind we're dealing with the top 7%. Okay? Now, if there's 7% above, and keep in mind that the area underneath one of these density curves has to equal 1, right? Then this opposite area, essentially has to be 1 minus 0.07, or in other words, 93%, or 0.93, okay? And as a left-tailed area that goes to the left of the score that we're interested in, this 0.93 is what we want to plug into our norm.s.inverse function. So, how much area is actually to the left? It's not 7%, it's 0.93 based on our picture. To find the appropriate z-score, this uses norm.s.inverse, and we plug in area to the left. So this is the critical part. We have to make sure we're plugging in the left-hand area. So we would use norm.s.inverse, plug in the 0.93, and then that's the only argument we need if we're using norm.s.inverse. Okay, so the appropriate z-score associated to this picture, right, not on the actual measurement x scale, but on a z-score axis, the appropriate value would be 1.47, right? And remember, we can use the x equals sigma times z plus our mean to convert this back to the appropriate measurement value. So this would be equal to standard deviation 7.6, our z-score is above, plus a mean of 35. So if we were to label that axis, this transition point should occur somewhere around 46, right? More precisely 46.2. And again, if you want to skip the conversion part, you can do norm.inverse, plug in your probability to the left, but then also provide the mean and the standard deviation. You'll get the same answer. When dealing with the top k%, top 20%, top 30%, remember the main idea is to just think about, if this is the percentage to the right, compute what the percentage to the left is going to be, and then use your standard process for percentiles. Okay? Now, as you get a little bit more comfortable with this, you may realize that, all right, if I'm shading a region to the right with a particular percentage, and I want the score that starts that region, you can do this little trick. Just use a norm.inverse and then use 1 minus p, right? Because the 1 minus p is secretly computing the left-hand area over here. And this will give you the same answer. Okay, so the last bit that I want to talk about is finding the middle percentages. I'm going to present two different ways of doing this. One is just to use the norm-inverse command twice, and the other is using something called the margin of error approach. The margin of error approach is going to be very important because it lays the foundation for how we compute confidence intervals, technique later in class. Okay, so what we're going to propose here is we want to be able to find what we call the middle k% of a normal distribution. And when I say the middle, essentially what I'm doing is trying to find the most likely k% of scores. And remember, with your density curves, the higher the curve, the more likely a score in that little region is to occur. So the most likely scores are going to be the ones right smack dab in the middle, because these are the highest values for our density curve. So we want to figure out, where does this middle k% start and stop? Notice we need to find 2 scores in order to do this. Okay, so let's jump over to our Excel sheet. We're going to click onto our next sheet here, middle 88%, and we're going to do the following example. So we have X measuring the damages that we would incur if a fire hit our warehouse. We assume it's normally distributed. Here we have a mean of 130,000. I'm just going to put this in a separate cell, so if I want to, I can cell reference this. A standard deviation of 50,000. And what we want to do is find the scores that mark off the middle 88% for this distribution of fire damages. Okay, so again, usually what we want to do here is draw a nice picture. So here's the picture that I started to draw. We've got a normal distribution. Here are our scores of damages. We're dealing 50,000, 100,000, 150, etc. You'll notice that the mean here is right around the 130,000 that we specified, and the width is determined by the standard deviation of 50,000. Right? So we have a probability in the middle here of 0.88. So what we want to do is figure out, well, where does this region start on our axis, and where does this region stop? Okay. So approach 1 is to find the lower and the upper scores separately. So what we would think about is we would finish labeling our picture. So if we have 0.088 in the middle, this essentially means we have 0.12 or 12% that needs to be equally distributed among the 2 tails, the tail on the right, the tail on the left. So 12% split into 2 gives us 6% that we would put into each tail. Now we can think about the left-hand boundary and the right-hand boundary and how we would find these percentiles just using norm.inverse, right? So for the first one, it's pretty simple, right? The middle region starts at this score where there's 6% to the left. So all we would do here is use a norm.inverse with 6% in our mean and standard deviation. All right, so our first argument is going to be the area to the left of this left-hand score, which is 0.06. So we'll jump in. We could do, I'm going to skip the z-score part. I'm just going to do norm.inverse. It asks me for a probability, so I'll do 0.06. My mean here I can cell reference as the 130,000, and my standard deviation I can cell reference as my 50,000. So this would tell me roughly 52,261. This would be where my left-hand score should be labeled. Now the right-hand score is a little bit different. All right, so we add the 0.06. Now we want to find this right-hand score. So we're going to focus on how much area is to the left of the right-hand score. Right? And if you think about it, you get the middle 0.88, but you also get this additional 0.06 to kind of complete that leftward tail. And if you sum these two pieces together, it gives you a total area to the left of this right-hand piece of a 94%. Okay? This is also equivalent to 1 minus the 6% that should be in the right-hand tail. And so what we're going to do is just use a norm.inverse, but using this percentage, the 0.94, inside of our input. So this would be norm.inverse. Our probability is going to be 0.94. We put our mean, which we're just going to cell reference, and it gives us our upper score. Okay, so our old picture, we would have somewhere around 52,000 as our lower score. That's where our middle 88% would start, and we have somewhere around 207,000 as our upper score. This is where it would stop. So basically what this tells us is that 88% of the time we would expect our fire damages, should a fire hit our warehouse, to fall between 52,000 and 207,000 in terms of our damage. Okay? Now we can do this using a margin of error approach, and what essentially does is takes advantage of sort of the symmetry that we have inside of a normal distribution. So each one of these normal distributions is symmetric about its mean. So what we can do, since we know the mean, this is provided when we're talking about our normal distribution, is just kind of focus on, since these are mirror images of one another, how far should I move to the left and to the right from our mean in order to kind of determine the left-hand point and the right-hand point. So it turns out this has a very simple simple formula to determine this margin of error, this ME as we're going to call it. There's a special z-score, which is going to be an input from our norm.s, or an output from our norm.s.inverse, right? So this is going to be a percentile for the standard normal distribution. And then we just multiply by the standard deviation of the normal distribution that we care about. So the main thing is in finding this z alpha over 2 value. Z alpha over 2 is essentially the z-score with 1 minus alpha over 2 probability to its left. And we'll talk about what alpha means in a second. And so it's a specific percentile. So we'll use our norm.s.inverse to figure out what that z-score is. Okay? So using our approach, we need to define what alpha is. Okay? So if we're dealing with a middle k percent, then alpha is essentially going to be the remaining percentage. All right, so in our case, k is equal to 88%, so alpha is going to equal to 12%. And I kind of talked about this when we were filling out this picture. If 88% is in the middle, how much is left over? Well, we've got alpha, which is 12%. And then the idea is we need to split that into two pieces. So alpha over 2 ends up being the 6%, let me write it this way, alpha over 2 ends up being the 6% that we end up labeling our tails with. Okay, so you'll notice in our picture, alpha over 2 is going to be the amount in each one of our tails. Alpha itself would be the sum of those two values. Okay, so alpha is going to be 0.12. Z alpha over 2, by our definition, is going to be the z-score with 1 minus the 6% probability to its left, or in other words, the 0.94% to the left. Okay, and we can find this by using a norm.s.inverse. Right. So this is going to look like norm.s.inverse. And built into the notation is a reminder to use the standard normal distribution, right? This is a z-score associated to this measurement alpha over 2, or this 6%. What we want to do is do 1 minus the alpha over 2 value, so 1 minus 0.06, and this will give us the appropriate z-score that we need to use in our margin of error formula. So we just found this value here. All right, so margin of error, generally speaking, looks like sigma times our z alpha over 2. In our case, our sigma is 50,000, and the z alpha over 2 we just found was, let me click in here, was 1.555 if you round. I'm just going to cell reference it. So this tells us that the margin of error we want to use for this approach number 2 is 77,738. Okay? And now based on that value, we can determine what the edge pieces are just by starting at our mean. Remember, our mean was 130,000. And then either adding or subtracting the margin of error to get to each side. So in the case, if we want the left-hand point, we take 130,000, subtract that margin of error we just computed. If we want the right-hand point, we would add the margin of error we just computed. Okay? So we can do this to get the starting and stopping places of our middle 88%. We'll take the mean and subtract our margin of error. And then same type of idea, but this time we're going to add so that we move to the right. And you'll see that we end up with the same lower and same upper scores. So it's really important that you understand and know how to use both of these methods. The margin of error approach is going to shed a lot of light on our confidence intervals that we'll discuss later in the course. And just using norm.inverse furthers your understanding of how the norm.inverse command works and how you can use it to find a bunch of different types of percentiles. Okay? So here's a procedure that I recommend maybe you put on some flashcards and start learning, because again, it's going to match up very closely with our confidence interval procedure that we work with later in the course. So to find the middle k% of a normal distribution, we define alpha to be the missing percentage. So this is the amount in the middle. Alpha will be the amount in the tails. So if k is represented as a decimal, alpha is really just 1 minus k. Find z alpha over 2. So this is a z-score with a particular area to the left. Now, the reason we're focusing on the left is so we can use our norm.s.inverse to compute this z-score. Okay? Essentially, what this is it's the z-score that has alpha over 2 in a right-hand tail. Once you use norm.s.inverse to compute this z alpha over 2, you can compute this margin of error. And that's really just the special z-score, which we'll eventually call a critical value, times the standard deviation of the normal distribution. Once you know your margin of error, you can find the two scores that mark off the middle. The one to the left will be your mean of the normal distribution minus the margin of error. The where your middle k% stops will be the mean plus your margin of error. And this is exactly what we did when we looked at approach 2 here. So the middle k%, k in this case is 88%. So our alpha value is the missing percentage, or 12%, and then alpha over 2 is 6%. So when we computed our z alpha over 2, we took 1 minus the alpha over 2 value, so 1 minus the 0.06. Plug that into the norm.s.inverse, and it gives you the appropriate critical value, or z percentile, that we need to use. The margin of error just took that critical value multiplied by the standard deviation of the normal distribution. And then to get the left and the right-hand points, we took the mean and we subtracted that margin error for the one for the left. And then for the right-hand point, we took the mean and we added the margin of error. Okay? The general formula ends up looking like mean minus critical value times standard deviation for the left-hand point, mean plus critical value times standard deviation for the right-hand point.